Hi, I'm Jeff. This is my video on the Girvan-Newman algorithm. Um, I'll just go over a brief premise of the algorithm as well as my implementation on the dataset of Zachary's Karate Club. So, the Girvan-Newman algorithm, named after Michelle Girvan and Mark Newman, is a hierarchical method used to detect communities in the graph, depending on the iterative elimination of edges with the highest number of shortest path that go through them. Essentially, the algorithm is the process of repetitive calculations of edge between the centrality of all nodes and cutting the edge with the highest centrality. In pseudocode, you repeat until no edges are left. Calculate the edge betweenness for every node in the graph, meaning that every node in the graph becomes the root, and then you remove the edge with the highest edge betweenness. You recalculate it, or else there'll be severe errors if you don't, for all remaining nodes, and then all the connected nodes are considered communities. This method works because groups are separated from one another, revealing the underlying community structure of the network. In sentences, edge betweenness works as the following. For every pair of vertices in a connected graph, there exists at least one shortest path between the vertices, such that in our case, for an unweighted graph, several edges that the path passes through is minimized. The betweenness centrality for each vertex is the number of these shortest paths that pass through the vertex, as mentioned before. After calculating edge betweenness for all nodes in the graph, edge values are added together respectively. I'll get to that. That might seem a little bit confusing, but I'll get to that later. If specific edges are bidimensional, meaning that go both directions, divide the sum by 2. The most important step for the Girvan-Newman algorithm is calculating the edge betweenness for every node on the graph. But first, the while loop must be instantiated so that the algorithm repeats until there are no more edges to be cut. Then we run the network X's edge betweenness centrality function, and the first step is to determine the shortest path for every node and assign the values to the respective node. A visual formula is shown in the image below. So, as you can see, it's a little bit cropped out, but node A is the root, and you're just trying to find the shortest path between node A and all the other nodes. So then at the very end, you add them, and you can see that A to D to C, it's a little cropped out, my bad, it's just 2. So the next step is to find the value of each edge in the graph. Start from the bottom of the converted graph picture below. So when you do the shortest path on a graph, you might want to consider doing it in this structural format so that it's easier for you to calculate edge betweenness. You understand what I mean for a second? Divide the above node's value by the bottom node's value, getting a fraction for the value. From there on out, the edge values are the previous edge minus previous edge value plus the node it leads into value divided by the previous node. That seems confusing, but as you can see here, for the first edges, you want to do 3 divided by 6. That's going to give you 0.5. And then from here to here, you would do, since we need to find the previous edge value, so it's 0.5 plus the node it leads into 2. Since we're trying to find this edge, it leads into F. Well, leads from F if you're looking down here, and divided by the previous node, 3. So it's 2.5 divided by 3. And there you go. That's 0.833. Sorry for the bad wording, but 3 examples you'll understand it, hopefully. The result is a completed edge betweenness graph of the single node as a root. This needs to be done for all nodes in the graph. The second to the last step is to add the respective edge values together. If the edges are bidirectional, as I said before, divide the edge values by 2, and finally cut the edges with the highest value. Here's a little walkthrough of an example of where we would use the Girvan-Newman algorithm. I suggest watching this video right here. But in short, I'll just quickly summarize it. This is not my work. Keep that in mind. But this is my just my summary. Above is a super simple yet effective graph to help guide us through the Girvan-Newman algorithm. So A, B, C, D, E, F. So it's pretty simple. Sorry. So our first step is to choose a root node and use the shortest path on the graph. After that, we reformat the graph in a more helpful structure. The first step is depicted below. So as you can see, we chose A as our root node, and we converted it into this structure that I mentioned before that will make our lives much easier. Then we have the next step is to calculate the edge values between the method, as I mentioned before, and the key components. Below is a completed edge between this of node A and the graph. Take a minute to look through that. Make sure you understand it. 1 divided by 3, it's 0.33. Then 1 plus that edge divided by this node, which is just 1, so it's just 1.33. But take a look at this part. So then repeat that for all nodes B, C, D, E, F. That's what you should get. Then we add all the values together to get the final graph. As you can see, you have all those edges, and they're added all together respectively. Do not mix them up. And by the end, you should get something like this. You put them on the original graph, and since you can go from A to B and B to A, you divide, and so on and so forth for all of them. You divide all the values by 2, so you should get something like this. We can see that the 4 of the edges have exactly the same value, and that coincidentally, those values are the highest of the bunch, resulting in 4 cuts to effectively split the graph. And that was just one iteration of the Girvan-Newman algorithm. Obviously, we could continue this until all the edges are cut up, but it's ultimately up for the user to stop the while loop, or give it a condition to produce an optimal result. So there you go. We have 3 clusters. So here's my implementation of it. My dataset was the karate dataset, Zachary's karate dataset. You can probably just look that up. You'll find a bunch of tutorials on it. Some of the algorithms it uses is kind of like wonky, but you understand why. I realized midway through my implementation that we had to run the algorithm exactly once, since we only wanted 2 communities or clusters. So that basically just my code just trickled down to just a couple lines of code, meaning that it's really just max cut. But obviously, if you want to do this for a more complex graph, it would work much better. So here we calculated the edge between us with the network x function. Since BW is basically just an array of those values, as you can from previous ones. It's just an array of some of these values, and so here we see that we try to find the max values, and it's stored in here, and so we remove all those edges related to that edge. So here's my analysis of what happened when I applied it to the Zachary's Karate Club dataset. So when we plot the newly cut graph shown below, we notice a small variance between the result and the ground truth. It turns out it gets an accuracy of around 94.118%, missing nodes 2 and 8, which happen to be, I think, around these ones. And they're typically missed by a lot of the algorithms. The advantages to this algorithm are that the fact that you can derive more and more communities out of a single graph, if so desired, and it works for unweighted and weighted graphs. However, it lacks the ability to accommodate data points which are distance-based, such like k-means or agglomerative. Here's an analysis of what went on in my algorithms. I used k-means, spectral, and agglomerative, and community detection. Community detection is just Girvan-Newman algorithm. So it does a small variance. That's because like this one, k-means and agglomerative missed 1, and spectral missed because spectral and community detection of Girvan-Newman algorithm missed 2. So it's a little bit less accurate than the rest. That's about it. Thank you. Sorry if I got some things wrong, and sorry for my stuttering. I'm not very used to these presentations. I'm just a high school student, but yeah, I hope you guys enjoyed. Please make sure to maybe just watch the video I entailed earlier. It's very helpful. I understood it and it helped me a lot. Thanks.